Okay, I think we can start. So if you, Cristian, I will just quickly introduce you, and then I stop sharing and I leave you the stage and you can share. So I close this. Okay. So we can start. Welcome everybody to the LMFL seminar session of first session of April. The speaker of today is Cristian Marchioli, who will talk about point particle simulations of complex turbulent dispersed flows. And I quickly introduce him, and then I leave him the stage as usual. So Cristian Marchioli is an associate professor of fluid mechanics at the University of Udine and editor of Acta Mechanica. In 2011-2015, he served as chairman of the cost action on fiber suspension flow modeling, and since 2018, as coordinator of the MSCA ITN project, Next Generation Computational Methods for Enhanced Multi-Phase Flow Processes. Professor Marchioli is also member of the Scientific Council of the International Center of Mechanical Science, where he coordinated several advanced schools on particle dynamics and turbulence. His research interests involve multi-phase flow modeling, from small-scale particle-turbulence interactions to large-scale modeling of gas-solid, gas-liquid flows. He has edited the book Collective Dynamics of Particles from Viscous to Turbulent Flows, and he has contributed to ERCOT-DAG's best practice guidelines for computational fluid dynamics of dispersed multi-phase flows. Professor Marchioli has published more than 60 papers and 150 conference proceedings on multi-phase flow modeling and simulation. He has also delivered several invited and keynote lectures, among others the 20th Meta Conference in 2011 and the 13th International Conference on Multi-Phase Flows in Industrial Plants at the Conference on Dynamics and Particles of Flows in 2014, and the 3rd International Conference Numerical Methods in Multi-Phase Flow in 2017. And the last one is the UTM Symposium of Turbulent Structure and Particle Turbulence Interaction 2020. It is with great pleasure that I leave the stage to Cristian Marchioli for his presentation. Cristian, I stop sharing my screen, and you can start sharing yours.
Okay. So let's see if what we did a few minutes ago works.
Yeah, we see your screen in presentation.
Okay, thank you very much, Francesco, for this kind introduction and for inviting me to deliver this seminar, which is going to be about point particle simulations of complex turbulent dispersed flows. And you'll see in a minute what I mean by complex. In fact, they are not so complex as some of you might imagine. The basic idea of the presentation is to show you how we can start from a very simple approach in which particles are modeled as points, couple this approach with an accurate resolution of the flow that we are interested in, and use this tool to gain some physical understanding of dispersed flows of applicable interest. So let me start from this image. This is not the picture of a swimming pool, the bottom of a swimming pool in a nice and sunny summer day, but it's just a 2D slice taken from the direct numerical simulation of homogeneous isotropic turbulence, showing the particle number density distribution. And as you probably know, this distribution is highly non-homogeneous. And there are regions, the greenish or yellowish ones. I am colorblind, so I'm sorry if I mistake colors every now and then, showing regions of strong particle accumulation that are known to correlate well with the high strain and low vorticity regions of the flow. In this case, the non-homogeneity of the distribution is due to the inertia of the particles. And this feature is common to somewhat more complex flows. I'm trying to change the slide. Okay. For instance, wall-bounded flows. What you see here is an animation of a turbulent flow in a channel laden with inertial particles. You can observe the non-homogeneous distribution in the bulk of the flow, but also wall accumulation, which is due to the well-known effect of turbophoresis, which is bringing our inertial particles to develop a peak of concentration well into the viscous sublayer. Now, this feature seems to be common to many, if not all, particle-laden turbulent flows, and is driven by the tendency of the particles to deviate from the fluid streamlines. And in the previous slides, this tendency was determined just by particle inertia, which can be parameterized by the Stokes number. As you know, probably this is computed as the ratio of the particle relaxation time to the flow time scale. Now, what we can do in order to study preferential concentration driven by inertia is to start with the simple setting possible, with the simplest setting possible, which can be obtained by using a dynamical model in which our particles are treated and modeled as points with a spherical shape. Now, if we stick to this limit, and we assume that the only source of bias is inertia, we can make use of very well validated and widely used equation of motion for each individual particle that we release into the flow. This because we are in the very low particle Reynolds number limit, so we can use the Stokes flow with the suitable corrections. Our particle will be much smaller than the grid size. And when we have to account for the forces that drive particle motion, we also have very well validated models, at least for the most important forces, that is drag, when inertia is the main ingredient. And so within this approach, everything we need to know about our particle is its trajectory in time and its velocity. Now, when we combine this very simple model, actually the simplest model, to an accurate resolution of the flow, which is the one we can get numerically through a direct numerical simulation, we can get some physical understanding about how particles interact with the turbulence at the particle scale. And again, in a turbulent flow, this would be a sub-Kolmogorov scale. So here I'm showing you an example of this physical understanding that we can get. This is a snapshot of the particle distribution referring to the channel flow simulation I showed you before. And here we make a close-up view in the wall accumulation region, where particles are rendered as dots, and these dots are colored by the vertical, or actually wall normal velocity of the particle. So you see here, oops, sorry. I hope you see the pointer. You see here a bunch of particles which are moving away from the wall, so re-entrained in the outer region of the flow, whereas the purple particles are moving to the wall. The color map in the background is showing you the streamwise fluid velocity, which is the velocity in the direction perpendicular to the screen, whereas the arrows, I hope you are able to see them, are giving you the distribution of the velocity, of the fluid velocity in the cross stream plane. And I hope you are able to see here the presence of two recirculations, which are the footprint of a quasi-streamwise vortex. It's actually the footprint of the legs of this vortex, which are generating an ejection of low momentum fluid in between, and this is the fluid motion which is entraining the particle away from the wall, and two sweep motions which are bringing the particles to the wall. So this is the type of interaction which is controlling the transport of the particles to and away from the wall. Now, this is driven solely by inertia in this case, but this kind of interaction can be observed also in different flow configurations. In particular, here, I want to bring you the attention to an interesting application which we examined some time ago in collaboration with Ugo Piomelli and Wen Hu. That is the rotor wing brownout. So brownout occurs, for instance, when an helicopter tries to land on an arid and dusty soil, and you see that this generates a cloud of dust and sand, which prevents the pilot to have a clear view of the landing area, and this can cause very harmful incidents. Now, what we can do, we can try to simplify and simulate the flow generated by the rotor wing, and this can be modeled as a periodically forced turbulent jet, which is impinging on the solid wall, which represents the soil. And if we do so, we have a very nice replica of the real flow that is characterized by several structures. We have a series of primary vortices that you see here, labeled as P1, P2, P3, and P4, and so on, which impinge on the wall and then move radially away from the impingement regions. And these primary vortices interact with secondary structures which are generated near the wall and also give rise to separation regions. This is an animation taken from the simulation made by Hu and Piomelli a few years ago, in which you can see the primary vortices, you can see where separation occurs at, and also the formation of the so-called rib-like vortices. So you see that now the structure of the flow gets complicated. I hope you're able to appreciate the movie fluently enough. And of course, then everything moves radially away from the impingement region. And clearly, the sand and the dust particles will interact with this flow structure. Okay, there are some small problems in advancing with the slides. Anyway, the question we asked ourselves was about the mechanisms that govern particle resuspension in such a flow. And to simulate this problem, just one slide of equations, we actually relied on large eddy simulation rather than DNS. However, the grid resolution in this case was very close to that of a DNS. So all the relevant flow structures with which the particles could interact were solved. And this flow solver was coupled with our simple dynamic model, in which particles are treated as points. And here we stick to the one-way coupling limit. That is, we consider dilute suspension of particles. Not because two-way coupling or collisions are in general not important at all, but just because, again, we want to keep the simulation setting as simple as possible and see what we can learn from our model. In addition, here, what matters is the effect of turbulence on the particles and their resuspension rather than particle feedback on the turbulence. And I can give you later more details about this. Now, this is an animation of particle resuspension that we observe in our flow. Particles are initially placed on the bottom wall, and you see that they start interacting with all the structures, and it is clear here the effect of the primary vortices in resuspending the particles. However, already from this qualitative animation, you can see that some particles actually execute small jumps away from the wall and then are redeposited, and another fraction of particles is able to remain airborne. So we see that in particles that are subject to the same initial condition actually exhibit different behaviors. And here we have discriminated between two different types of behaviors. That of type A particles, which are able to reach the outer flow region and remain airborne for a very long time, and the behavior of type B particles, which only execute small jumps as they move radially away from the impingement region. So clearly, this different behavior must be due to different type of interaction of these particles with the coherent structures of the flow. In this case, the flow is characterized by the presence of rib-like vortices, which form in between primary vortices. And these give rise to the formation of streaks of fluid velocity and to sweeps and ejections that are very similar to those that I presented before for the channel flow simulation. So this is the actual representation that we have of these structures from the flow at a given time. This is at 1/4 of the forcing period of the jet, and the structures are visualized by the, I think it's the vorticity here, but you see here more or less the primary vortex and a bunch of coherent structures near the wall, which are reproduced here to this schematic. In particular, we see here that an ejection is located where a low-speed streak occurs, and this is the region where, of course, particles can be entrained away from the wall. In this case, the low-speed streak, so the region where the ejection can occur, is characterized by a negative value of the radial fluid velocity fluctuation and a positive value of the one normal fluid velocity fluctuation. So we have tried, of course, to understand the type of interaction that these particles have with structures. And an important feature of this flow is that the near-wall coherent structures, and in particular the rib-like vortices that I just described, are lifted up at the moment flow separation occurs. So this lift-up process is more or less shown here. It happens between 1/4 and half the forcing period. So I hope you are able to appreciate that the structures are now detached from the bottom wall. And this is again a schematic representation of what happens. So the vortices here are, of course, tilted upwards. Now, in order to understand the different interaction of type A and type B particles with these structures, we look at the flow field that the particles sample. Now, on the left here, we have a plot that refers to type A particles. On the right, the plot refers to type B particles. So airborne particle and not airborne particles. The color map shows you the vertical fluid velocity fluctuation sampled by the particles as they move. And in particular, this is the distribution of the velocity fluctuation in time, which is the vertical scale, and along the radial direction, which is the horizontal axis. The color map is such that positive values of the fluid velocity are in red, and these correspond to strong ejections, whereas blue, of course, is negative values, so strong sweeps. The thick solid line that you see here is just showing the trajectory of the primary vortex as it moves radially away from the impingement region. But what matters here is these dashed lines here that you see in the two plots. These represent the initial or the location at which the two different types of particles execute the first jump away from the wall. So this is the first detachment. And what you can readily observe is that type B particles leave, so are entrained away from the wall earlier than type A particles. And in particular, they are leaving the wall before flow separation occurs, whereas type A particles leave the wall exactly when flow separation occurs. Now, we can also see what kind of radial fluid velocity distribution these particles see. So it's the same plot as before. So now the color map refers to the radial fluid velocity fluctuation. So you see that before flow separation occurs, type B particle do not sample a region where they can find a strong enough ejection that can sustain long enough their resuspension, and so they are forced to move again to the soil. Whereas type A particles, you see, they are able to find this very dark blue region, which corresponds to a much stronger ejection that is also occurring during flow separation. So when the coherent structures are entrained and lifted up. So this is the type of mechanism that allows type A particle to move farther away from the wall. And of course, this is the type of interaction that we can get out of our simulations. Of course, we can look further into this interaction and ask ourselves, how come this type A particle can then remain airborne for a very long time? And again, this has to do with the lift-off process of the coherent structures, all right, which proceeds, of course, in time as the flow moves radially outwards. And if we look at the schematic in a few words, what happens is the following. When the structures are lifted up, particles that are entrained in an ejection are actually pushed radially in the direction opposite to the movement of the periodic vortex. And in particular, so the ejection brings the particles against the primary vortex that is behind, and they interact with the upwash side of this vortex. And this upwash side brings particles further away from the wall. These are the type A particles. For those particles that are actually entrained in a sweep during the flow separation, the sweep is pushing the particles towards the preceding primary vortex and interact with the downwash side of this vortex. And this is what brings these particles, the type B particles, again to the wall. So there is a sort of fence effect which can explain the different behavior, which is summarized here. So again, this was just an example of the kind of information we can extract from a simple modeling of the flow, yet I would say realistic enough, at least for this case. Everything I told you so far is due solely by an inertial bias. But of course, in many applications, inertia is not the only source of bias. Additional sources of bias that make particle deviate from the fluid streamlines can be due to non-sphericity of the particle, to the formability of the particle, or to their ability to move in an active way through the flow, so to their motility. So in this case, the complexity arises from the fact that the anisotropy of the particles adds to the anisotropy of turbulence. When this happens, we cannot stick to our simple model anymore, and we need to add more particle functionalities to it. So it's not enough anymore to know everything about trajectory and translational velocity. We need to also know about the rotation of the particle. If the particle is non-spherical, we need to take into account the effect of this non-sphericity on all these variables. For instance, through the aspect ratio of the particle, if the particle has a simple non-spherical shape like an ellipsoid. Of course, we need also to know the orientation of the particle within the flow, especially if we are interested in the motion of motile particles. And if we consider the formable particles, we probably have to include some connectivity constraint into our model. Now, I would like to present you one case in which we are adding these features, and in particular deformation, and another case in which motility is important. So let me start by the first one. So the first case is the dynamics of flexible fibers in turbulent channel flow. This is just one slide to remind you that the results I'm going to show are relative to numerical simulation of the Navier-Stokes equations coupled with Lagrangian particle tracking. And these are the simulation parameters for the flexible fibers. So we examine different Stokes numbers, so different inertia, these different aspect ratios of the fibers, so different elongation. And we always compare our results with the reference case of spherical particles. The first case I'm showing you is the simulation of this flexible fiber in turbulent channel flow. This is just an animation of the flow we are interested in. In this case, the fibers are deviating from the fluid streamlines, not only because they have their own inertia, but again, because they are non-spherical and they can deform under the action of the fluid. Just one slide, I think, or maybe a couple, to give you a few details about the modeling. So the flexible fiber is modeling using this bead model, which has been used and developed some years ago and used quite widely. So the fiber is just a chain of short segments. It could be also spheres, which are connected by ball and socket joints. Now, each segment composing the chain is smaller than the Kolmogorov scale in the flow, but the whole chain then is longer than the Kolmogorov scale of the flow. Because we have sub-Kolmogorov elements constituting the chain, we can solve for each segment the first and second Euler law. And of course, here we have to take into account also the rotation of the segments. And on the right-hand side, we need to account also for the relevant forces which are acting. So for instance, for a translational equation of motion, in addition to drag force, we need to take into account also the force that is generated on one segment by the neighboring segments, which we call xr+1 and xr. Of course, these forces also generate additional torques that act on the segment, in addition to the hydrodynamic torques, which are here split in two contributions, T and H. So T is the hydrodynamic torque due to the fact that the rotation of the segment can be different with respect to the rotation rate of the local of the surrounding fluid, and H is the torque due to the velocity gradients that are acting around the segment. All of this, of course, is coupled with the connectivity constraints that we must impose in order to let the segments rotate with respect to each other without exhibiting a relative translation. Okay. Okay, here just a summary of the simulation details, this is a close-up view of the fiber dynamics in a region in a small part of the channel. Okay, so this is a near wall region where you can appreciate the type of deformation that the flow is inducing, and also, if the movie is smooth enough, the type of dynamics that the particles are undergoing, and you can see many particles that are doing this sort of pole vaulting motion. Now, among the many different statistical observables that we have examined, I would like to focus on a couple that refer to the formation of the fibers. So this slide is quite busy, so I will go through it picture by picture. So let me first focus on this PDF here. This is the PDF of the solid angle alpha, which is the angle that is formed between two neighboring segments. So you take the symmetry axis of one segment and the symmetry axis of the following segment, and you compute, one can compute the solid angle between these two. So if alpha is equal to 0, that means that the two segments are perfectly aligned. So alpha equals to 0 is the condition that we have when the fiber is actually fully stretched. Of course, if alpha is different from 0, there will be some deformation, so some relative orientation between the segments. Now, the first two PDFs I would like to draw your attention to are the green one and the red one. These are the PDFs that we computed considering just the fibers that are located in the near wall region, which we arbitrarily define as the region, as a region of thickness equal to 30 wall units from the wall. And the two curves refer to fibers that have different aspect ratio. Here, the aspect ratio is referred to the individual segment of the fiber chain. So one value is lambda2, the shorter and the smaller aspect ratio, and the other is lambda equal 5. So in the near wall region, you can see that the aspect ratio is not really playing a role because the two PDFs are almost overlapping, but the important point is that the PDF develops a peak close to alpha 0 angle. So it means that in this near wall region, fibers are fully stretched or actually close to the fully stretched condition. Not much deformability for them. If we now compute the PDF in the bulk region of the flow, so considering only fibers that are at least 30 wall units away from the wall, we have the black PDF and the blue PDF. So again, the two different aspect ratios. Quantitatively, the aspect ratio has an effect, but still what we find is that there is a clear peak in between 1 and 1.5 radians. So in general, this indicates that these flexible fibers are more deformed in the bulk region of the flow. And it could be intuitive to figure out that these different deformation dynamics are due to the presence of a strong mean shear near the wall and to an absence of this mean shear close to the wall, which is actually what we find in these two pictures here on the right-hand side, where we correlate the angle alpha, which, by the way, we average over all the fibers that we consider, so it's an average value of alpha, the one we are showing, to the span-wise fluid vorticity computed at the center of mass of each fiber. So if we compute this correlation in the bulk region of the flow, we see that the peak is obtained for values indeed between 1 and 1.5, corresponding to this peak of the PDF, and almost zero value of the vorticity, so the fluid vorticity here, all right? So at least small values of the span-wise vorticity. Whereas if we do the same computation in the near-wall region, the maximum correlation drops to values of alpha close to zero, corresponding to this peak, and much higher values of the span-wise vorticity of the fluid that in this region is very closely related to the mean shear. So this physical intuition is confirmed by this plot here. However, I have to mention that these results refer to, I would say, high inertia fibers. The Stokes number for a single segment is 30. The Stokes number for the whole fiber in this case is about twice this value here. So it would be 60. So inertia is very strong for these particles and for these fibers. So what happens if we consider a case of much lower inertia? And to show you this, I consider a different observable, which can be again related to the deformability of the particle, which is the fiber end-to-end distance. When the fiber is fully stretched, the end-to-end distance, of course, is equal to the complete length of the fiber. Otherwise, it is smaller. Now, what you show here are three plots that refer to fibers with different inertia, from the smaller one to the largest one, all right? In each plot, what I'm showing you is the behavior of the change of the fiber end-to-end distance as a function of the wall normal coordinate for the two aspect ratios that I introduced before. Now, the green curve and the red curve represent the actual behavior we get from the simulations, whereas the thin straight line is the end-to-end distance that it would have if the fiber was fully stretched. Now, let's focus on the plot on the right here. We see, in fact, that the actual end-to-end distance is far away from the fully stretched condition for both aspect ratios in the center of the channel, whereas it gets closer to the fully stretched condition near the wall. So this result is in line with the PDF results that I showed you before. However, if we decrease inertia, for instance, if we consider this plot over here, we see that a totally different behavior occurs. In fact, the fibers are closer to the fully stretched condition in the center of the channel, and they get more deformed when they are close to the wall. So it's a sort of opposite behavior. Now, I don't have the time to go too much into detail. Of course, this different behavior refers to a different accumulation pattern of the fibers in the near wall region, depending on their inertia. But the point I want to make is that here, when we combine the bias due to inertia to the bias due to the length of the fiber, so the non-sphericity of the fiber, and the bias due to deformation, we can obtain non-straightforward behavior that, at least to me, is quite interesting. Okay, after a while, when I'm on a slide, I cannot control properly the slide anymore. Now, I would like then to move to a different type of bias, which I already anticipated, which is motility. And in particular, I would like to focus on a specific case of motile particles, which are the so-called gyrotactic microswimmers. So these are microorganisms that are able to escape the fluid streamlines by swimming. And this swimming motion is determined by their ability to orient in the direction of gravity. So in this case, they are able to undertake a locomotion that results from the combination of a gravitational torque and a viscous torque. This is what we call gyrotaxis. The gravitational torque is due to the fact that within a cell of the swimmer, the center of mass, it does not coincide with the center of rotation, and this generates the gravitational torque, which in general counteracts the viscous torque. So this gravitational torque allows the swimmer to orient itself in the direction of gravity, and in particular opposite to gravity, to swim upwards and reach the upper layer of water bodies where the organism can make photosynthesis. So we are interested in the interaction or in the dynamics of these swimmers in a turbulent flow. We make a series of assumptions which are in line with the model I just presented. In particular, we assume that the swimming velocity is constant and that is always aligned with the orientation unit vector P. And so the equations of motion for the swimmers are the following. And in particular here, we use a very simple Jeffrey type equation for the time evolution of P, which depends on two terms. The first one is the reorientation term due to the gravitational torque, where the important parameter is this B, which is the reorientation time taken by the swimmer. And the second term is due to the action of vorticity, which of course can destabilize the motion of the swimmer. In our model, besides the reorientation time B, the other controlling parameter is the swimming velocity. And when these two are made dimensionless, they are termed the swimming number and the vertical stability number. So we fix the swimming number and we change the vertical stability number in order to consider both swimmers that are slow to reorient in the gravity direction or swimmers that are fast to reorient in the gravity direction. And the values here are chosen to scale with the time scale, sorry, with the Kolmogorov time scale of the flow. For instance, the slow to reorient swimmers have a reorientation time that is about 10 times larger than the Kolmogorov time scale, whereas the fast to reorient swimmer have a reorientation time that is 1/10 of the Kolmogorov time scale in our flow. Now, we have performed several investigations with these swimmers. Here, I would like to propose to you some results that refer to the dynamics of these swimmers in thermally stratified turbulence. In this case, we are generating a stably stratified turbulent flow by considering an open channel and imposing a constant heat flux condition on the top wall, which is a free slip surface, and an adiabatic wall condition at the bottom wall, where we also impose a no-slip condition. By enforcing different levels of thermal stratification, we can modify the mean streamwise velocity profile, which is shown here. So the thermal stratification level is quantified through the shear Richardson number. So Richardson equal to 0 means no stratification, which is this solid line here. And then the other two profiles refer to cases in which stratification gets stronger and stronger. And in particular here, you see that the profile is modified such that there is some mean shear acting within the flow at the largest stratification level. So this mean shear adds to the mean shear that we normally have at the bottom wall. And this corresponds to the formation of a thermocline. So a region where the temperature of the fluid changes dramatically, so very rapidly, and generates this potential barrier that the swimmers must interact with as they move vertically within the flow. These are three animations that shows you the evolution of the temperature field, and in particular, these are the two thermally stratified cases in which you can see the formation of the thermocline. And these are the equations that we have been solving. So again, it's the DNS here. And let's see what the swimmers do when they interact with this flow. So this is what happens when the swimmers move within an unstratified flow. So we release the swimmers from the midplane. This is an arbitrary initial condition. And you see that turbulence is strong enough to bring the swimmers all over the place, and in particular, also close to the upper surface. Here, the turbulent fluctuations close to the upper boundary are decreasing as we approach the upper boundary, and the swimmers can reach the surface. If, however, we consider the same situation, but with a strongly stratified flow, this is what happens. Here, I'm showing you the dynamics of the slow to reorient swimmers because it shows more clearly that the thermocline, which is located more or less here, is a sort of blocking the vertical rise of the swimmers. So these are prevented from reaching the upper layers of the flow. Whereas, of course, turbulence is able to bring them in the bottom part of the channel. So, of course, the concentration of the swimmers here will be much lower, and this decrease of concentration occurs exactly when this additional mean shear due to stratification was located. Now, the reason why this happens is that when the swimmers are interactive with the thermocline, they are not able to swim vertically upwards anymore, but they are forced to swim horizontally or downward again. And this can be seen very easily by looking at the components of the orientation vector. And in particular here, I show you the vertical or wall normal component of this orientation, PZ. So when PZ is equal to 1, it means that the swimmer is moving upwards in the direction opposite to gravity, which is the condition we would like to have in order to reach the upper layers of the flow. Here I'm showing you 3 different plots. However, each plot is showing the same thing. So the behavior of PZ as a function of the vertical distance from the upper surface. And for sake of time, I would like to draw your attention to this plot here on the right, which shows the behavior of PZ for the strongly stratified case, Richardson 500, and the 3 different types of swimmers that we consider. Now, what you see is that if the swimmer is able to quickly reorient in the gravity direction, in fact, the thermocline is not strong enough to disrupt its vertical motion, and it moves, so the swimmer, on average, can move quite steadily in the vertical direction throughout the entire channel, with the exception of a very tiny and thin region just below the free surface, and of course, a thicker region in the bottom part of the channel, which, however, is not of big interest here. The important or the interesting result is actually observed for the intermediate gyrotaxis swimmers, which is this dashed line here. Because as you can see, exactly where the thermocline is formed, we have a strong reduction in the value of PZ. So it means that our swimmer is not able to move vertically anymore. And this is confirmed by the distribution of the horizontal component of the orientation vector, so Px. When Px is equal to 1, then the swimmer is moving horizontally. And again, if you focus on the strongly stratified case and the intermediate gyrotaxis case, you see that this value of Px is strongly increased when the swimmer meets the thermocline. So this kind of disruption of the vertical motion explains why the swimmers cannot move upwards. Now, if I have time, Francesco, can I have another 5 or 6?
You can take 5–10 minutes.
Okay, okay. I would like to now move to another application in which there is an interface between 2 fluids, and the interface plays an important role. So in the previous application, there was this free surface that I sort of neglected, and I didn't spend too much time talking about the role of this free slip surface on the motion of the swimmers. Here, in this problem, there is an interface that is formed between a carrier fluid and large deformable droplets. The case we are considering here is a liquid-liquid suspension in which, for instance, the carrier fluid is water and the droplets are oil droplets, which are brought about by the turbulent flow, and they can undergo deformation. In addition, we are also considering the dispersion of small spherical particles with very, very tiny inertia that can interact both with the carrier fluid, but most importantly, with the surface of the droplets. The case we are considering here may be of interest for applications such as scrubbing processes or frog flotation processes. Now, this is actually a 3-phase flow in which the main characters are turbulence, the deformable droplets and the particles. Here you see actually particles that have been trapped by the droplet, and we are only showing the particles and not the surface of the droplet. And of course, there is a strong interaction between each of these phases with the other. In the results I'm going to present to you, we are considering some effects that result from this interaction. For instance, the modulation that turbulence produces on the droplets through the shear stresses, and the feedback of the droplets on turbulence through the capillary stresses. We are considering possible turbophoretic effects of turbulence on particles, and the fact that when particles are deposited on the droplet, on the surface of the droplet, of course, they have to behave taking into account the local variation of the curvature. There would be additional important effects like possible momentum exchange between the particles in turbulence and local changes in the surface tension of the droplets induced by the particles in a way similar to what surfactants are known to do. But these two effects are ruled out of the picture for the time being. Just a few slides about the methodology. Again, we consider DNS. In this case, we have to suitably modify the Navier-Stokes equation in order to take into account the effect of the droplets on turbulence. So there will be a turbulence modulation induced by the deformation of the drops. And the Navier-Stokes equation is then coupled with the Canillard equation, which provides the time evolution for this order parameter phi, which we use to discriminate between regions of the flow where the carrier fluid is located, which are the regions where phi is equal to -1, from regions of the flow where we are inside a droplet, where phi is equal to +1, to points within the domain which are occupied by the interface, characterized by phi equal to 0. So depending on the value of the order parameter, we know exactly where we are within the flow. Again, in order to start with something simple, we assume that the fluid and the droplets have the same density and same viscosity, and we consider constant surface tension at all times during the simulation. The flow solver is, I think I forgot to mention, but all these DNS simulations come from a pseudospectral solver, which is coupled with the usual equation of motion. In this case, in addition to drag, we consider this capillary force, which is the force that models, in our simulation, the interaction between the particles and the interface between the fluid and the drop. So I beg your pardon if I don't give you too many details about the force. I prefer to explain how the force works. This is a purely attractive force, and it works in the following way. So this red line here is the interface. So on the left, we are in the fluid phase. On the right, we are inside the drop. This pink layer is the transition layer where the order parameter changes its value smoothly from -1 to +1. And this is the line that tells you how the force works. So this capillary force starts acting as soon as the particle touches the interface. So when the center of the particle is 1 radius away from the interface, the force is immediately switched on. It has its maximum value, and of course pushes the particle towards the interface. Then the force becomes 0 when the particle is exactly on the interface. So this is the equilibrium position. So no force is acting as long as the particle stays on the interface. If some fluid event is trying to bring the particle away from the interface, then the force wants to restore this equilibrium condition. These are the simulation parameters for those who are interested. Nothing special here. I just draw your attention to the simulation parameters that we consider. The flow Reynolds number is not very high, but this is because we need a grid resolution that is much higher than that we could use at the same Reynolds in a single phase flow. And this is to ensure an accurate reproduction of the interface dynamics. we have considered situations in which the droplets have different deformability, which is here parameterized by the Weber number, but that's not really a very important aspect. And this is the Stokes number of the particles. So as you can see, these are particles with very weak inertia, but this weak inertia will play some role, as you will see. So we studied two different processes which characterize the particles. The first process is the capture of the particles at the drop interface. So one capture event is shown here in this inset. So you see here we have a bunch of droplets which are deformed, and we have made here a close-up view of some particles which are rendered here as points, and the arrows show you the velocity of these particles. So these particles are brought to the interface of the drop by a sort of jet-like fluid motion, which is impinging on this portion of the drop. And here, the surface of the drop is colored with its local curvature. Once the particles are captured, of course, they are subject to the interfacial stresses, which are rendered by these red arrows here. And as you can see already from this picture, we can see that these particles will be moved away from the capture position. Now, we wanted to provide a sort of topological characterization for these capture regions. And in order to do so, we used the surface divergence. This is the divergence of the fluid velocity computed along the surface of the drop. So besides its formal definition, the physical meaning is the following. If we have a sink of velocity at the interface, which can be produced by a jet of fluid moving away from the interface, then the surface divergence is negative. If we have a source of velocity due to a jet impinging on the interface of the drop, then the surface divergence will be positive. Now, this is the PDF of the surface divergence sampled by the particles at the moment they get captured at the interface. So what you see here are two PDFs, the light gray and the dark gray one, which refers to the two different Stokes numbers indicated here. And since the two PDFs are more or less overlapping, you can see that inertia is not really playing a big role in determining a different sampling of the divergence. Whereas the thick black line that you see here is the PDF that we get if we assume that the droplet surface is covered uniformly by the particles, so fully covered by uniform distribution of particles. So even in this case, which I call the tracer case, you see that the PDF is not symmetrical. It's somehow negatively skewed with a peak close to the zero value of the surface divergence. However, when we add a little bit of inertia, the PDF shifts to the right and exhibits a clear peak in the positive semi-plane, so about surface divergence about 1. So this confirms the physical intuition given by the previous picture that it's these jet-like motions that preferentially brings the particle close enough to the surface to be captured by the drop. Once particles are captured, of course, they can be trapped for a very long time on the surface of the drop. And here it is very important to provide a realistic distribution of the particles and of the particle patterns that form long time after the capture. In here, you see that the situation that we get if we allow the particles to overlap and not interact with each other. So the particles are moved along the surface by the interfacial stresses and end up forming clusters. In this case, clusters are not of the inertial type I showed you at the beginning of the presentation, but are driven actually by the fact that the particles are forced to stay at the surface. And they have these filamentary structures because the particles do not see each other and can overlap. So there is no excluded volume effects accounted for. However, when we account for these excluded volume effects, you see that the distribution becomes more uniform, I would say more realistic. And in this case, these excluded volume effects are reproduced and forced by particle collisions. Clearly, and I think I have to stop because I'm looking at the time, this case is important, or reproducing the right distribution of the particles is important for different aspects. For instance, we know that very small particles trapped on the surface of the drop can produce local changes in the surface tension and therefore can change locally the deformability of the particles. So clearly the deformation, the change in deformability that we get by including excluded volume effects will be different from those that we get when particles can overlap. And this will produce a more realistic model of these surface tension changes that it is desirable to include in simulations. Now, I had a couple of more statistics, but I think I said what I wanted to say. I don't have real conclusions. I just want to thank you very much for your kind attention and for the patience. And I would like also to thank all these people here, these colleagues that have helped me and sometimes driven me towards all of these problems that I surveyed. So I hope that I could make my point, and of course I'm happy to take your questions and try to answer the best I can. Thank you very much.
Thank you, Cristian, for the great talk and kind of the overview about several studies in particles, in point particles with different characteristics. And if there are any questions, you can just unmute your mic. I will start with the questions which we have in the discussion. I can report them, or if you want, you can also have a look at them by yourself. So the first one is, do you use Kolmogorov timescale in your Stokes number? What is the density ratio between particle and fluid? And what are the assumed ratios of particle to Kolmogorov scale?
Okay, so let me see. Okay, so this is, I think it's a general question. Yeah. So if I understand correctly, the context, let's say, of the question, in general, for the wall-bounded flow, we are not using the Kolmogorov time scale to provide the Stokes number, because of course we have a change of the Kolmogorov time scale with the distance from the wall. So usually the flow time scale is based on the shear velocity and on the viscosity. Of course, we have also, let's say, checked what would be the local value of the Stokes number if we normalize the particle relaxation time over the Kolmogorov time scale. And well, for the simulation that I have presented, the local Stokes number would change by a factor of 10, more or less. So indeed, if we compare the particle relaxation time with the local Kolmogorov time scale in the flow, the inertia, the local inertia of the particle would change a lot if the particle is in the near-wall region, or if the particle is in the center of the channel. I hope I answered the first part of the question. Density ratio.
Just a second, Cristian, because I think, Jim, you can, if you want to interact, because.
Okay.
Okay. So I just came on. The question, when you quote your Stokes numbers, one has to interpret it, and you know, you always make the statement the larger Stokes numbers means greater inertia, but that's only relevant if you know what the normalization time scale is, what the flow time scale you're normalizing. So I think it's really important that you quote what that time scale is. So if I understood correctly, since you're not using a turbulence time scale, if I understood you correctly, I don't really understand what time scale it is you're using. You said something about shear and viscosity, but in order to understand what Stokes number of 10 versus 1 means, we need to understand what that flow time scale is that you're using.
Yeah. So as I tried to say before, we are using a viscous characteristic time scale for the fluid. So it's going to be the kinematic viscosity over the shear velocity or friction velocity squared. So this is the usual.
That's a near wall time scale, obviously.
Yeah.
Yeah, so that works for near wall flows, but you were showing some flows like in isotropic turbulence. So you must change your definition of the time scale depending on the flow, I guess.
Yes, exactly. So I think if I'm not wrong, now I might be a little bit tired, but if I'm not wrong, the only result I showed with homogeneous isotropic turbulence was in the, I think, very first slide. And indeed, you're right. That Stokes number is not defined as the other Stokes numbers I presented later. That is defined on the local, on the Kolmogorov timescale of the flow. So you cannot compare directly that value with those I presented for the wall-bounded flows.
Yeah. So okay. So carry this on just a little bit farther. And when you're doing the wall-bounded flow and you're using the wall-bound the near surface, the viscous layer timescale, then those particles are outside the viscous layer and they're well up into the inertial layer, Z plus greater than 30, as you were showing. That's not an appropriate timescale anymore for Stokes number, is it?
Yes, you're right. And that's the other thing I wanted to, or try to explain before, in the sense that, of course, we can always, in our simulations, compute the local value of the Kolmogorov scales, be it the length scales or the time scale. In this case, we are interested in the time scale. So we can always measure the Stokes number, normalizing the particle relaxation time with the local Kolmogorov scale. If you do that, you will find that the same, or the Stokes number defined in this way, so the Kolmogorov-based Stokes number, would change by at least 1 order of magnitude if you are close to the wall or away from it in the bulk flow. This is an important point, in fact. The values of the Stokes number I'm giving is a sort of macroscopic parameter, meaning that I try to, let's say, associate the inertia of the particles with just one macroscopic parameter. But as you said, the picture is even more complicated if I do this Kolmogorov-based scaling, because in fact, the inertia of the particle is not, if you want, absolute. It changes within the same flow depending on where you are, and this is due to the anisotropy of turbulence. This is one of the complexities that arise, and this is true.
Absolutely. So that was sort of where I was going with this, that it's more complicated than what you're suggesting by a single Stokes number, right? Okay, so the second question that I have, I'll quickly ask and then let other people, so I don't hog this. One of the questions I've always wondered about particle trajectory studies is I sort of imagine sort of comparing a fluid particle, which is the fluid trajectory, and a real particle, and then characterizing, sort of the time scale where the trajectories separate from each, a statistical sense, like a Lyapunov time scale or something like that. And I've always wondered if anybody has done any studies where they try to quantify the time scale where those two trajectories, the particle and the fluid particle trajectories, deviate, and then try to characterize those time scale, the separation time scales in terms of, either the particle relaxation time or flow time or some mixed time scale. So what is that time scale? And I was just wondering if anybody has done those kind of studies. It's just something that I've wondered for a long time.
Yeah, well, let's say that this deviation, of course, depends on, let's say, this Stokes number, or whatever you define it. And we have sort of investigated this deviation, not just from a fluid streamline, but also when you change the inertia of the particle. And this is important for simulation techniques like large eddy simulation. So this deviation is actually occurring on a I would say characteristic time scale, which is related to the Stokes number. I could not tell you, if it's one Stokes number, a fraction of it, or larger. But the important point is that this deviation accumulates in time. So the trajectory will become different and more and more different because of
Yeah, no, I understand. I get what you're saying. Stokes number, of course, is not a time scale. It's a ratio of time scales. But really, the reason, again, I'm sorry for hogging the questions, but I have an application in mind. There are many situations where if like I do drug dissolution type work, drug studies work, and drug particles follow streamlines, and then they release molecules and so on. And when the particles start to deviate from the streamlines is very important for those kinds of problems. So I was trying to characterize, I was wondering if anybody's characterized sort of some kind of a characteristic timescale that says that under certain conditions, particles will remain on the trajectory for certain periods of time and then start to deviate, that kind of thing. So I was just wondering if anybody's done those kinds of studies.
Exactly this one now I cannot recall, but I think that this is for a tour, maybe the type of flow, so the flow regime is also important, because in turbulence, of course.
Oh yes, for sure, absolutely.
This is somehow related to the extent of the fluctuations that the particles are subject to. So yeah, so it's a bit complicated.
Okay. All right, thanks. I'll
stop. Precise answer right now. Sorry.
Yeah, all right, thank you very much.
There must be something, but it's my ignorance, I would say.
Yeah, no, thank you.
Thanks to you.
Okay, is there someone else who wants to ask a question? Just feel free to unmute your mic and ask your questions.
I have a quick question, Cristian. This is Christos.
Christos.
Yeah. The concentration or preferential accumulation of particles in various places and so forth. But of course, even in the turbulence itself, there is a preferential concentration of vorticity or preferential concentration of acceleration, because turbulence is intermittent. How do you relate these two types of intermittency, the one in the particles and the one in the flow? And do you need to relate them? Is there any relation?
I'm not sure I understood exactly the question.
The number of preferential concentration of particles, for example.
Yes.
Yes. So particles go somewhere and they don't go somewhere else.
Okay.
The flow is not uniform. The turbulent flow has vorticity somewhere and doesn't have vorticity somewhere else. Are the two related in general?
Yeah, I would say that, yeah, it depends on the specific features of the flow, of course, because of course I'm aware that there are many different mechanisms that have been proposed and you have proposed one, of course, the sweepstick mechanism that have been proposed to explain preferential concentration. I would say that, from an engineering point of view, or from our point of view, let's say, what actually matters is a way to somehow quantify this preferential concentration, regardless of the specific turbulent mechanism which is bringing it. So this is one, let's say, of the messages I've tried to convey. Then, of course, depending on the type of particles that one considers, I would say that, and on the particle parameters, probably different mechanisms are or have a different relative importance. We didn't try to do, even though it was in our mind, but time is limited. We didn't try to investigate in detail what would be this relative importance, which I guess is what you mean by relating this different mechanisms. Depending on the conditions, the different mechanism can be of importance, but we didn't try to discriminate.
Even though you mentioned this engineering approach, which I think is very good, you tried nevertheless sometimes to explain some mechanism in terms of particular relation with structures, those hairpins or whatever. But they could come in bundles, or they could come alone, and that could change your mechanism. That's why I also mentioned intermittency.
Yeah, this is true. I would say that for the type of flows that we have considered, and for the models that we have used, of course, we have certain specific structures which form, and we are interested in those that form near the wall. So these are somehow a sort of universal type of structures. Of course, if we move away from the wall, then we might have different type of, turbulence, and intermittency will also be of different nature, and these would probably have an effect on the preferential concentration. We never focus that much on the preferential concentration away from the wall. So our mind was, let's say, more focused on what happens near the wall. And again, I am sure that devising this relation would be interesting. I cannot give you a specific answer for the cases I've presented and for the cases I experienced.
Yeah. Thank you, Cristian.
Oh, you're welcome.
Some more questions? Then I can ask a couple if that's fine. Yeah, the first question. Oh, sorry. So the first question is related to the model. If you use a model for like resuspension of particles, when you consider, for example, you show the particles resuspending in the vertical structures created by helicopters. Do you use like a resuspension model or?
Well, not really, in the sense that, of course, we are somehow again simplifying the situation there, in the sense that we are placing the particles close to the wall, and we consider that they are already available for detachment. So from a practical point of view, we know that this brownout is, or the main issue with the brownout is this cloud of airborne particles that is formed. So it is not really an issue, or there's no real question about the possibility of particles to detach. They of course detach, and probably the mechanisms that control detachment are not really of big importance in this case. But what we want is particles that are available for detachment, that can be detached by interacting with the coherent flow structures. And what we are really interested in is actually what they do once they are resuspended. So not where they are very, very close to the boundary, to the bottom boundary, but when they are able to interact with these rib-like vortices. In fact, the main processes occurs when there is this lift up. So the particles need to be lifted up together with the structures, and the structures, are located with some distance with respect to the wall. So more than one particle radius, for instance. But we saw that in our simulation, placing the particle a little bit more than one particle radius away from the wall was enough to allow lift up. Then, of course, we did also some analysis about the type of resuspension that we get, and we tried to estimate the resuspension fluxes to some pickup model, but I didn't have time to show the results.
And the second question was related to the last topic you showed, where you had like the three-phase flow, and you talked about the model which you consider for particles getting close to the droplet. Mm-hmm. And so can you talk about the regimes under which such a model is supposed to be valid? In the sense, I mean, I think you are assuming that once the particle gets close to the surface of the droplet, kinds of wettability plays a role. So the particle gets wet and it remains there. That's why you say it does not move. It gets attracted to the interface. So I mean,
yeah. Of course, I mean, you can think of all these effects, and in fact, the capillary force that we are considering somehow embodies this effect. Of course, we are not able to reproduce explicitly the deformation of the surface of the drop, that occurs when the particle is trapped. So for us, the particle is so small that, let's say, somehow we are unable to reproduce this with our model. There are some constants in the force that somehow reproduce macroscopically, if you want, the effect of this wettability. What we can say is that, of course, we have to assume that the particles like to stay on the surface, right? So they are hydrophilic, if you want, rather than hydrophobic. And indeed, the equilibrium position for them is to stay exactly on the interface. Whatever tries to move the particle away from it is counteracted by this capillary force. As I said, the model is simple. I'm not saying that you know, it's the best or the most accurate, but probably it is enough to capture some you know, some of the physics, of the fundamental physics. Then, of course, even the type of interaction that we have included neglects some important effects. So, for instance, if you have two trapped particles that come together, the neck that forms, the portion of interface that forms between the two, will probably act as a sort of spring which tends to move away the particles from each other. So, in fact, in reality, they might not even touch, right? So, these effects are out of reach for the model that we use. Of course, this is something that is going on, so we hope we can study further the problem and see if this kind of interaction, which has actually been studied by Lorenzo Botto and his group, modeled by Lorenzo Botto and his group through a sort of force, interaction force, can somehow provide results which are in line with these results that we got by imposing collisions, which I think I would expect the same type of macroscopic behavior. So a more uniform distribution of the particles on the surface of the drops.
So if I'm allowed to jump in and ask another question related to this topic. So it seems to me that your model, which keeps your particle on the interface, implies that you have a 90 degrees contact angle.
In practice, yes.
Is that true? So, and then if even I think if the contact angle would not be 90 degrees, your particle position would be, would shift away from the theoretical unperturbed interface.
Mm-hmm. Yes, exactly. It's true. The condition that somehow we imply with this model is that the particle likes to stay exactly with a 90-degree contact angle. As I said, we cannot replicate the type of interaction of the particles with the interface if it moves away from this. This is only partially somehow represented by the capillary force through some constants, but of course it's not explicit. So this is a limit of the model, clearly.
Yeah, so it depends very much on the two fluids that you are using.
Yes, exactly. Also, yeah, that's true. And in fact, we have made some assumptions also on the, as I mentioned, on the density and the viscosity. The idea is not to say, okay, look, this is the last or the ultimate, but at least we believe that even under these assumptions, some physical phenomena can be understood. And for instance, as I mentioned, we were interested in understanding what could be the potential effect of these particles on the surface tension changes if we can model this in a way that is similar to what is done with surfactants. And that should be the case. Clearly, that's a long way to go. And as you said, there are some effects that we are missing. Yeah.
Okay, thank you very much.
Just a follow-up, sorry. That's it's a very interesting topic, so it calls for questions.
I have nothing to do after this. So
can you go back to the slide where you show the model?
Oh, I don't know why after some time I have to use these arrows.
Yeah, that's it. Basically, if you would just in case, I mean, if you want to consider like a physical correspondence of a model for perfectly hydrophilic particles, what you would observe, I think, is that the particle, as soon as it arrives to the interface, it kind of gets absorbed or somehow fully wetted by the droplets. So basically, you form kind of a thin film of liquid all around the particle, and then the more you get dragged through the interface, the more this kind of particle, once it crosses half of the particle cross the interface, capillary forces tend to restore the interface and push the particle inside. Mm-hmm. So in that case, if you want to consider perfectly hydrophilic particles, I think you can just modify the inner part of the force. Instead of saying that the particle gets restored back to the interface, you can just give a negative slope and allow the particle to get in the droplet, to dive in. And that would be kind of a model for the solution inside the droplet.
So you would change the sign. That's
or change the slope eventually. Because basically you get capillary forces. If the particle is fully covered by the liquid outside, then those kind of curvature after a certain point, it's gonna push the particle in, trying to restore the minimum energy, you know.
Yes, but I'm afraid that if I do this, then the particle will just go inside the droplet. So
so
it will move somewhere. I'm afraid. I don't know if this is what you were proposing.
It does.
This would happen. This would happen.
That it does. That's why
it would either remain outside or will be ingested. The 90 degrees contact angle, it would stay near the interface, or on the interface exactly. So if the contact angle is somewhere in between, okay, maybe there's some other equilibrium position possible.
On the other hand, I think that one possible, let's say, mechanism that could support the use of this model is that clearly here, what can take the particle away from the surface is a strong fluctuation. So locally, we can have some peak in the drag force, which overcomes this force, and in that sense, the detachment would be almost immediate. So in this case, the time scale with which the particle moves away from the interface would probably be much shorter than a sort of time scale for the interaction, between the particle and the interface, in which this wettability plays a role. So it's like, suddenly taking the particle away. So, and we do observe this kind of behavior. So some particles can be, taken back into the mean flow or even inside of the droplets. But of course, these are just rare events. Clearly, if I change the distribution of the force, I would see more and more particles go inside of the droplet. Yes. This kind of formulation, we just took it as it was proposed by Lorenzo Botto and Etelai and Lishuk, as I mentioned here. And so, okay, we just said, let's apply this and see what happens. Of course, we can improve our model in many ways, and this could be one way to go.
Basically, you would consider different regimes.
Sorry, say it again.
Basically, you would consider different regimes, different kinds of...
Yeah, exactly. Different type of interactions, let's say, or between the... Yeah, exactly. Yeah.
Yes.
Okay. Any more comments, questions you want to ask? If there are questions, just feel free to unmute your mic and ask it yourself. Or you can write in the chat if you have other questions. I can report them.
Yeah. Hello. Ciao,
Cristian. Go ahead.
Hello. Yeah, one question concerning this last problem you analyzed. Because I think you solve the equation sequentially. So first you solve for the phase field and then for the particles. What is indeed the influence of solving them sequentially for these particles that perhaps once you advance the phase field, then the drop is moving away and the particle cannot follow immediately this movement, but can just follow it after.
Let's say we are using a very short time step, so this kind of mismatch between the position of the interface and the position of the particle is very small, and it's actually always restored by the force. So we can advance in time. I would say the particle in the same way as we advance the interface. So clearly we cannot put the particle, let me say, in the same point of the interface time step after time step. So at one time step, the particle is at a certain position. The next time step, this position of the interface will have moved in the 3D space, and we cannot ensure that we place the particle in the same position. What we can ensure is that it's more or less in a surrounding region, and we do that by shortening as much as possible the time step, which, by the way, in the case of collisions is also small because of the collision time, and then by putting the particle again on the interface thanks to the force. But yes, there is a small, I would say, mismatch between the interface position and the particle position that we cannot ensure because of the model, because it's fully Eulerian for the fluid and the droplets, and let's say for the Lagrangian approach that we can use, there is no way for us to say if the point on the interface goes from A to B, then the particle must go from A to B. This we cannot do.
This is perhaps something that should be taken into account concerning the previous discussion for when you change the model for hydrophilic or hydrophobic. Could be something that perhaps should be taken into account if you want to slightly change the model, because then this force is not keeping the particle very close to the interface, but perhaps the particle can really.
The force, of course, is not keeping the particle steadily on the interface, but it could give a slight,
fluctuation.
Yeah, because that's not perfect. But I would say, from what we have seen, that this kind of shift, short shift away from the interface is not that important. So of course, we have made a test on the time step, and we have made sure that with the time step we are using, for instance, we don't see differences in the cluster formation. So after a while, the clusters are the same if the time step is small enough. So this kind of analysis was done, but clearly things are not perfect, as you understood.
And if I can, the very last thing concerning the helicopter, you mentioned that you use a large eddy simulation, although perhaps it was close to a DNS.
Yes.
Indeed, what is the influence, in your opinion, of the subgrid scale model on the particle dispersion? Because I think you didn't add, right,
no, I didn't
scale.
Of course, there is some filtering of the flow field. However, in the structures that are controlling the resuspension of the particles in this case are, I would say, well reproduced, because their spatial and their length scale is long enough. So I don't think that they are, or the rendering that we have of these structures is, let's say, bad, or it's too much affected by the subgrid scales. In addition, of course, well, I could give you the Stokes number, but yeah, maybe in ways I should have paid also more attention in the way it was defined. But the inertia of the particles is itself a filter. So in this case, particles, or in any case I presented, of course, that particles interact with the structures that are somehow larger than a certain length scale and live longer than a certain time scale. Too short structures, or I should better say, too short fluctuations in the flow are naturally filtered by the particles. So what we did in the LES was actually to filter only those fluctuations in the flow field that would have been nevertheless filtered by the structures. So even though I am always, paying a lot of attention in the effect of the subgrid scales on the motion of the particles, I think that in this case, especially, when the particles are away from the near wall region, I don't think that the subgrid scales play an important role here. Especially, if you are interested in the physical mechanism. Then if you tell me, compute the flux of particles that can be resuspended, probably I might be quantitatively wrong by a few percents because of the neglect of subgrid scale velocity fluctuations in the particle equation. But the main physical mechanisms are captured, and I would say even the percentage of resuspended particles would be somehow realistic if compared to experiments, which we didn't do. This is just my opinion based on the results that we get. So, I would be quite confident that in this specific case, first, we are not filtering too much, and second, because of the particle characteristics, these are sand particles, so density is much higher than that of air and so on. So the filtering, natural filtering of particles is somehow helping us in neglecting the scales. But yeah, that's in general, that's an important effect that should be accounted for and gives rise to this deviation of the trajectories that was hinted to before.
Yeah. Thank you.
Thanks.
So any more questions? Once again, feel free to unmute your mic or to write in the chat if eventually I can report the question. Okay, so it doesn't seem to be the case. So Cristian, thanks a lot once again for this very interesting presentation, which, as you saw, it gave rise to a quite lively discussion. And
it was almost longer than the presentation itself.
Yes, which is a good sign, by the way. Thanks. I would invite everyone to thank our speaker again, and I hope to see you all next week for another presentation. So thanks, Cristian, and have a good evening
to everybody. And have a good evening or good morning wherever you are, or good night. I don't know. Bye bye.
Thank you very much, Cristian. Bye bye.
Thanks. See you soon, hopefully.
Bye, Francesco.
In person.
Bye.
Thank you.